Thank you, everyone. My name is Michaela Cashman, and I am a biologist with the U.S. EPA in Narragansett, Rhode Island, at the Atlantic Coastal Environmental Sciences Division. My current research with the EPA looks at fate and transport, as well as ecological effects of emerging contaminants, such as active pharmaceutical ingredients, PFAS, and microplastics. But I did my master's degree at the University of Rhode Island, and it was focused on advanced oxidation processes for 1,4-dioxane in groundwater. So I'm here today to talk about the fate of 1,4-dioxane from a hydrogeology perspective. So you've heard this many times today. 1,4-dioxane was used as a solvent stabilizer for chlorinated solvents such as TCA. Trichloroethane and other chlorinated solvents were used as degreasers for large-scale manufacturing equipment, and dioxane was added to canisters of these chlorinated solvents to help them from oxidizing while being stored in canisters. So it's no surprise that so many of our known 1,4-dioxane contaminated sites are associated with chlorinated solvents such as TCA or TCE. Obviously, though, that's not the full story, and there are many sites here in the United States that aren't associated with chlorinated solvents. When we think of suspected groundwater contaminated sites, we think of chlorinated solvent spill sites, but we also think of landfills, laboratories that may have manufactured dioxane or used it in excess, as well as airports, gas stations, and so on and so forth. And while chlorinated solvents such as TCA and dioxane may enter the environment at the same location, many of their physical and chemical properties ultimately dictate where they end up in the environment. So I wanted to briefly talk about some of those chemical properties and compare them to that of TCA. 1,4-dioxane, you can see, I note here as 1,4-DX for the rest of the presentation. It's a cyclic ether, where TCA is not. Dioxane has a very high boiling point, much higher than TCA and higher than water. It has a very low vapor pressure. And then the two things below, log KOW and log KOC, those are partitioning coefficients, and they are essentially just ratios of two different substrates that tell us where a contaminant is likely to partition. So the KOW, or octanol water partitioning coefficient, shows us a ratio of whether something will be soluble in fat or soluble in water. You can see that for 1,4-dioxane, this is a negative number indicating that dioxane is really fully miscible in water. And that's quite different when you compare it to TCA. The log KOC is a partitioning coefficient showing us how likely something is to partition into soil, and this is normalized to a soil's organic carbon content. So you can see that TCA is actually very likely to partition to soil or organic matter in soil, where 1,4-dioxane really isn't. Bringing that back, you've heard this said before, but these properties kind of drive the reason that 1,4-dioxane is hydrophilic and completely miscible in water. Its preferential partitioning when it enters the environment is to partition, if we're talking about in the ground, we're talking about either the water table or pore water. Separate analytical detection techniques are needed for these two compounds, and that's part of the reason why for so many years 1,4-dioxane went undetected in the environment. And they respond very differently to remediation techniques. I wanted to drive that point home with a schematic that I adapted from a CERDUP report, number 2128, which is a bird's eye view of a contaminant plume where TCA and dioxane may exist. Groundwater has a natural flow to it, much like a river, but much slower. So this picture shows a source zone, or where a contaminant enters the groundwater, and then because of the directional flow of groundwater, we're assuming this flows left to right. TCA will start in the source zone, and once it enters groundwater, will slowly move with groundwater flow, but it may become inhibited or retarded by soil or soil organic carbon. Dioxane is much less likely to be inhibited, so once it enters the groundwater, it moves freely and quickly, which means that when we compare TCA and dioxane contaminant plumes, we often see that dioxane is much more dilute, but also has spread further and faster, resulting in these large dilute contaminant plumes. So as far as federal regulations, to repeat again, I don't work in drinking water, so I'm speaking on federal regulations from sort of an academic standpoint, but there are no established maximum or federal maximum contaminant levels for drinking water. There is a health-based advisory of 35 micrograms per liter for drinking water based in a lifetime cancer risk of 1 in 10,000. Or a 0.35 micrograms per liter based on 1 in a million cancer risk. There's also the risk-based site screening level of 0.46 micrograms per liter. 1,4-dioxane was included on the third and fourth drinking water contaminant candidate list, and it was also included in the third unregulated contaminant monitoring rule, which is referred to as the UCMR or the UCMR3 in this instance. And the EPA uses UCMR to collect data for contaminants that are suspected to be in drinking water and do not have health-based standards set under SWWA. So here's some of the data from UCMR3. This was a report put out or a publication by Adamson in 2017, but the UCMR3 surveyed nearly 5,000 public water supplies in the United States, and these data are solely for 1,4-dioxane. You can see the map on the left. Each circle represents a public water supply that was analyzed for 1,4-dioxane. A hollow circle with no color indicates that this site was tested, but the concentration was below the minimum reporting level, which was 0.07 micrograms per liter. The grade circles are above the minimum reporting level, but they are below the reference concentration. And the red circles are above reference concentration, which is 0.35 micrograms per liter, which goes back to that health-based advisory risk level. The same data is shown on the right, but we're looking in a bit different way based on occurrence, and it's separated by the size of the system. But all in all, of the nearly 5,000 public water systems that were reviewed, 21% of them were above the minimum reporting level, and 6.9% of these public water supplies were above the reference concentration. As of 2016, nearly or just above 34 national priority sites for the US EPA indicated that 1,4-dioxane was a contaminant on site. So when we talk about remediation techniques, the two big branches of remediation include ex situ and in situ remediation. Ex situ remediation is basically remediation that happens above ground or off-site. So we're talking about removing the contaminant or the contaminated media and treating it elsewhere. When we're talking about groundwater, this is often referred to as pump and treat. So contaminated groundwater is pumped out of the ground and treated off-site. Some of the known viable solutions tested both in laboratory and field scale settings with positive results include ex situ chemical oxidation using peroxide, ozone, and UV or titanium dioxide. These are advanced oxidation processes that rely on radicals to break down the contaminant in question, in this case dioxane. We also see ex situ remediation that uses aerobic bioreactors or sorptive resins. Advantages to ex situ remediation include they're very advantageous for sites with complex contamination histories. They're also very effective for shallow contaminant plumes, but they do cause quite a significant land disturbance, especially if the plume is very large that we're looking to ex situ remediate, and they require high energy output. So the opposite of an ex situ remediation technique would be an in situ or in-ground remediation technique. My master's focused on in situ chemical oxidation, so I have a personal bias towards that remediation technique. But again, we're looking at different oxidants that can be utilized to oxidize or break down 1,4-dioxane within groundwater. Other promising remediation techniques currently being used to remediate dioxane from groundwater include thermal treatments such as electrical resistance heating, steam enhanced extraction, or thermal conduction heating. These in situ remediation techniques, they can be less invasive. They often involve boring a well into, or a series of wells into the ground to pump your oxidant. They can degrade very high concentrations of oxidant if enough wells are installed and if the intensity of radical formation is present. And certain oxidants can oxidize chlorinated VOCs very well, so it's an effective remediation technique. But disadvantages to in situ remediation include that localized hydrology compromises in situ remediation techniques as well as co-contaminants, and it can be very cost prohibitive. Another series of in situ remediation techniques includes biological treatments. I separated these because their advantages and disadvantages are a little separate, but I know also that there will be someone speaking on bioremediation techniques later, but some of the processes used as far as biological treatments include metabolomic and co-metabolomic bioremediation, phytoremediation, and monitored natural attenuation. These can be, depending on the type of treatment used and the site conditions, they can be used together to degrade high and low concentrations of 1,4-dioxane, and they have less chemical input into the ground, but they have many disadvantages. One of them is that anaerobic bioremediation has not yet been proven effective in field scale experiments, so there's a need to maintain aerobic conditions, which can be very difficult in groundwater settings. It may cause phytotoxicity to plants that are being used to uptake dioxane, and it can be a much slower process than some of the aforementioned remediation techniques. I was asked briefly to maybe go over a case study of where dioxane is listed in a Superfund site somewhere in New England. So I know that there are people who will be speaking after me from the Department of Energy and Environmental Protection for Connecticut, as well as the Department of Public Health. So I won't go too far, but one of the current Superfund sites for 1,4-dioxane is in Durham, Connecticut. It's the Durham Meadows Superfund site. This is a classic example where a Superfund site was declared in 1989 for trichloroethane, but then it was reassessed in 2003 for dioxane. Connecticut Department of Public Health has a drinking water action level of 3 parts per billion in drinking water, but at selected sites while analyzing for dioxane, it was found that there was up to 26 parts per billion in untreated water, 12 parts per billion in residential drinking water, and one site as high as 1,400 parts per billion detected in a private well. So this remediation process has been twofold, where on site at the Merriam Manufacturing Company and Durham Manufacturing Companies, there was study area cleanups in 2015, which included removing and excavating the soil and carbon filtering of wells as a precaution. But as far as as far as the groundwater goes, groundwater is not being used in this town anymore as a potable drinking water. So there's an alternative public water supply given to affected residents, and they are still working. There's an ongoing construction program happening for the alternative water supply. So that's my brief presentation. Thank you.
I'd like to talk a little bit about occurrence of 1,4-dioxane in drinking water sources and finished drinking water. And like Michaela already showed these properties, so all I'm going to say here is that 1,4-dioxane loves to be in the water, and therefore it's difficult to remove from drinking water through treatment processes. I'll mention some of the processes a little bit later. In terms of sources, apart from underground storage tanks that have already been mentioned as a major source of groundwater contamination, the presence of 1,4-dioxane in personal care products leads to detection of 1,4-dioxane in treated wastewater, and also an important source of 1,4-dioxane in surface water, which is perhaps not as commonly thought of as a contaminated water supply. We see that industrial wastewater can contain very high levels of 1,4-dioxane. In some cases, that's because 1,4-dioxane is used as a solvent in certain industries like the textile industry or specialty chemical manufacturing. But the other thing that I think is really important to note is that 1,4-dioxane can also be generated as a byproduct unintentionally in processes that involve ethylene oxide. And so ethylene oxide is an important building block in chemistry. And so PET plastics or the manufacturing of surfactants leads to 1,4-dioxane production as a byproduct. That I think is important also from a regulatory construct. Michaela briefly mentioned this also. 1,4-dioxane was an analyte in EPA's third unregulated contaminant monitoring rule. And in this activity, samples were collected between 2013 and 2015. And basically that included finished drinking water from public water systems that serve 10,000 people or more. So it didn't really give a good picture of the many small systems around the country, but it gives us a national perspective on occurrence in larger systems. It was a big effort. Almost 37,000 samples were analyzed from almost 5,000 public water systems, and EPA method 522 was used, which has a reporting limit of 70 nanograms per liter. So it's below the 1 in a million cancer risk level. So when you look at occurrence around the country, if we look at public water systems in this table, almost 22% of the sample, almost 22% of the participating public water systems had at least one detect of 1,4-dioxane above the method reporting limit, and 7% of the systems had at least one sample above the 1 in a million cancer risk level. So it's a widely occurring contaminant. And one of my students generated this map where we separated the drinking waters that were derived from groundwater in red and the ones derived from surface water in blue. And so you can see that in total, 1,4-dioxane occurred above the 0.35 ppb level in 37 states. And let me see here, moving forward, if we think about this from a population impact, these public water systems serve almost 30 million people. So, one thing that I always think about is it's not just occurrence maybe as a percentage, which is something that can sometimes look not so impressive, but if we think about the number of people who are really impacted, and that number is significantly larger than the one we often talk about with PFAS, where the often quoted number is 6 million people experiencing drinking water with PFAS and PFOA levels above 70 nanograms per liter. So I'm in North Carolina, and what's interesting and concerning here is that the majority of 1,4-dioxane was found in drinking water derived from surface water, and 9 of the 10 highest concentrations measured in the country for surface water derived drinking water were in North Carolina. If we go to the more heavily impacted systems, so I picked here the 3.5 microgram per liter level, which would be the 1 in 100,000 risk level. We can see the states. In total, there are 12 states that had systems experiencing 1,4-dioxane levels above 3.5 micrograms per liter. And the top states are New York and California, and then North Carolina. And the different colors indicate, again, where 1,4-dioxane is found in groundwater primarily, and where is it found in surface water, which is the green color. So you can see that in North Carolina, things are different from New York and California in the sense that all of our contamination is in surface water. So if we zoom in on North Carolina, we find that the watershed that's most heavily impacted, I don't know whether you can see my cursor, but you know, that watershed here is where all the big blue dots are, is the Cape Fear River watershed. And about 1 million people, a little more than 1 million people, are receiving drinking water that is impacted by high levels of 1,4-dioxane. Some of the dots are outside of the Cape Fear River watershed. This is an interbasin transfer type of situation where these communities also get at least a portion of their water from the Cape Fear River. When we look at 1,4-dioxane levels in a small system here in North Carolina, this is the town of Pittsboro. So this would have been a location that wouldn't have been captured by the UCMR3 activity. We see, you know, very high levels of 1,4-dioxane in the finished drinking water. And when we look at the annual average concentrations, you know, they look, here we can see in 2014 and 2015, it's between 15 and 20 micrograms per liter. More recently, it's dropped somewhat, but you know, what we also see here is a very high peak. These are weekly composited samples. So this was at least for a duration of the week that on average people were drinking water with over 100 micrograms per liter 1,4-dioxane as recently as fall of 2019. You know, this water treatment plant is a conventional surface water treatment plant. They do add some powdered activated carbon, but as we've heard already, activated carbon is not effective for removing 1,4-dioxane. So you can see here that the orange data and the blue data sets are essentially identical. They're slightly offset, which represents the residence time in the drinking water treatment plant. But there's no meaningful removal of 1,4-dioxane here. Oxidation is a process that does work. And so in Wilmington, North Carolina, both raw and settled water are ozonated. And you know, that leads to about a 2/3 transformation of the influent 1,4-dioxane. But the levels are still elevated. You know, we just heard the MCL for New York. For the majority of the time that we measured samples here, the values were above the 1 microgram per liter level, although the average is quite close to the New York target. So, you know, one thing that we were very curious about here in North Carolina is what are the sources of 1,4-dioxane in surface water? Also, what's the temporal and spatial variability in 1,4-dioxane concentrations? And, you know, before we even could get started on answering those questions, we needed to answer the question, what analytical method is appropriate to determine 1,4-dioxane in a wide range of water matrices. We were interested in analyzing at least treated wastewater and river water and drinking water. And when we met with our DEQ, you know, the first question was, well, you know, there's no good method that can analyze 1,4-dioxane in this wide range of water matrices. So first thing we needed to do was develop a method. And then the final question is, you know, can the data we collect actually affect change and lead to lower inputs of 1,4-dioxane into surface water? So we developed a new method for the analysis of 1,4-dioxane. We based this on heated purge and trap GC mass spec. And it's an isotope dilution method. So we add deuterium labeled 1,4-dioxane into samples to account for matrix effects such as ion suppression during the mass spectrometric detection. Our method is very simple in terms of sample collection. We now basically can do this with 40 ml EPA vials that are headspace free. And in fact, we now have a method in place where we can analyze volatile organic contaminants together with 1,4-dioxane very sensitively and very rapidly. Our calibration here goes from 0.15 to 300 micrograms per liter. And we basically have excellent linearity over this range. We validate our calibration with a standard from a second source, and our blanks are below the 50% of the MRL, most of the time well below that. And the real sort of proof for our method was based on matrix spike recoveries from 4 different types of water matrices, and they all ranged from anywhere from 85 to 115%. So this would be quite acceptable, and there weren't really meaningful differences among the 4 matrices. We did this matrix spike experiment at 2 different spike levels. And this basically shows we can measure 1,4-dioxane in a wide range of matrices. And this was published in 2016 in ESNT for those of you who would like to take a look. So we then went out to the field. So this was a fun project for our group. We also worked together for a year with DEQ here in North Carolina. And we sampled many sites mostly from bridges using these bridge samplers that we designed. And so here are some results. So let me just orient you. This here is the Cape Fear River watershed. There's the Haw River in blue, the Deep River in this color that I can't quite tell. It's probably gray. And then the Rocky River in light green, and then the Cape Fear starts where the Haw and the Deep merge, and it's indicated in purple here. And then each of the circles in these sections that we pulled out of the map, the circles have different colors. Green would be 1,4-dioxane levels below 0.35 micrograms per liter. Yellow would be between 0.35 and 3.5. Orange between 3.5 and 35. Red between 35 and 80, and then purple above 80. And so, one thing I want to point out is there are only 2 spots on all of these maps where the color was green. One is on the Rocky River, and one is up here on the Haw River before the first wastewater treatment plant discharge that's indicated by this triangle here. And from there on downstream, all of the dots are either red or orange or yellow in color, meaning that in essence, the entire watershed is impacted apart from the very headwater region. In total, we initially surveyed 47 locations, bracketing 14 different wastewater treatment plant discharges. In the end, we trimmed that down to 32 sites that we then monitored for a period of a year. In total, this represented 600 samples approximately upstream and downstream from 9 wastewater treatment plants. And so what we found was, in essence, there were 3 important sources. One was in the Deep River. So here's a wastewater plant in this segment 2. Very high levels in the creek into which the wastewater treatment plant discharged, and then a jump in concentrations from a median of 2 to a median of 20 micrograms per liter in the river at this point D6 here. Another location is up here on the Haw River. Again, if we look at this highlight 5, the green dot is just upstream of the black triangle where the wastewater comes in. And then we go immediately to very high levels. So here we go from a median of 0.2 to a median of 76 micrograms per liter in the river over the period of a year. And the third wastewater plant is a very large plant. And here we went from an upstream median concentration of 1.8 to 26 in the river downstream. At other locations, wastewater treatment plants did not significantly increase the 1,4-dioxane levels. So here are a couple examples of that. I should point out that a typical 1,4-dioxane concentration in municipal wastewater prior to discharge to the river might be on the order of 1 to 3 micrograms per liter as a result of the use of consumer products like detergents and shampoos. So these levels are all way above this because of the industrially impacted wastewater discharges. So what we found here is that 3 municipal wastewater treatment plant discharges were the primary sources of elevated levels of 1,4-dioxane in the Cape Fear River watershed. There was high temporal and spatial variability. One thing I didn't really point out here is what quantity can actually contaminate the entire watershed. And I gave a presentation a few years ago at Yale at the AESP conference that was called 50 pounds of 1,4-dioxane a day, enough to contaminate a whole watershed. And in fact, we see typically mass flows on the order of tens to maybe just above 50 pounds per day in this watershed. So in terms of policy challenges, there is no federal drinking water standard. There's no North Carolina drinking water standard. But North Carolina, interestingly, does have a surface water quality standard in place. And it's a narrative standard that I copied down here, which basically says that for carcinogens, the level of a carcinogen in the drinking water supply should be below the 1 in a million cancer risk level. So based on that, in theory, we should have a regulation in place that that our DEQ could use to enforce a 0.35 microgram per liter water supply standard, but this is currently not enforced. So that's my presentation. I want to thank Catalina, who's up here, who did a lot of the field work, and May, who developed the GCMS method, and Amy McElroy, who you will hear about a little bit later, who studied biodegradation of 1,4-dioxane, and Zach Hopkins. And our work was funded both locally and through the National Science Foundation. And we work closely with municipal drinking water providers and our DEQ. And with that, happy to answer questions and also put in a plug for this paper, which we published last year. Linda mentioned emerging contaminants. 1,4-dioxane was first measured in the Haw River actually almost 40 years ago exactly, and we're still dealing with it today.
So today we'll be talking about the actions the Division of Drinking Water has taken on 1,4-dioxane. And before I get started, I definitely want to thank a number of my colleagues with the Division of Drinking Water, the Los Angeles Department of Water and Power, and the City of Monterey Park. So we've definitely heard this throughout the morning, but 1,4-dioxane was used as a stabilizer in chlorinated solvents, and we continue to find 1,4-dioxane with chlorinated solvents. It's present in a number of industrial and commercial applications. It's a byproduct of PET, and EPA has listed it as a possible human carcinogen. And actually in 1988, California added 1,4-dioxane to the list of chemicals known to cause cancer. Exposure pathways include ingestion of drinking water, inhalation of vapor, and dermal contact. So 1,4-dioxane has some pretty unique properties. It's short-lived in the atmosphere, and that's really due to the photooxidation. It's highly soluble in water. It poorly absorbs to soil particles. It mitigates rapidly in groundwater. It's relatively resistant to biodegradation and the subsurface. It's non-volatile. It definitely co-occurs with some chlorinated solvent plumes. It has a low molecular weight and non-ionic. And all of these properties really make it difficult to treat using our more common drinking water treatment processes like air stripping or GAC. So California established a notification level back in 1998, and that was based on EPA's initial health advisory level. In 2010, when EPA reduced their health advisory level, then the California Department of Public Health at the time changed their notification level to 1 part per billion. And what a notification level is just a requirement that water systems notify their public when they exceed that level. There's also a corresponding response level, which is 35 parts per billion, and that's where we ask that the source that exceeds that concentration be removed from service. And last year, we did request from OEHA to develop a public health goal. And this is our first step in developing an MCL. And the reason it's our first step is because when we do develop an MCL, it needs to be as close as practical to the public health goal. So we always start with establishing a public health goal and then can move on to an MCL. So some of the drinking water requirements at this point, for drinking water source, all monitoring is voluntary at this point, with kind of a few exceptions. But for potable reuse projects, we are requiring that the systems monitor and provide treatment. And I'll kind of talk about both, what we've done with drinking water and potable reuse. So starting with the drinking water, in California, we have monitoring going back to 1996. It was included in the UCMR round 3, and so we do have some data from that. And to date, 436 water systems have monitored. To kind of put this in perspective, if we developed an MCL, we'd have about 4,400 water systems that would be required to monitor. So we're looking at about 10% of our water systems that have taken samples. And our detection level is currently 1 part per billion. Because this is the same as our notification level, if you exceed the detection limit, you are required to do the notification. So since 2014, we've had most of our samples really occur in Los Angeles County and then in Orange County. And you can see 173 sources are impacted, and that actually impacts 56 different water systems. And the peak concentration is 29, which means that all of the sources are below the response level, but all of these sources are above the notification level. This is kind of a different way of looking at the data in the previous table. You can see this is the number of detections, and this is Los Angeles County. So clearly they are the most impacted, followed by Orange County, and then not too many in Santa Barbara or Monterey, but they are detecting it up there also. So we do have a few drinking water treatment projects in various stages of completion. These are all US Superfund sites, and they're doing multiple contamination treatment methods. And all the projects that we currently have going on are listed, and so some are operational at this point, and others are either in construction or still planning phases. Right now, the only treatment process that we have identified is UV-AOP. And typically what we're seeing is peroxide being used for the AOP. Here's a typical treatment process for 1,4-dioxane, and the only reason for the SAM separators and the cartridge filters upstream of the UV-AOP system is really to protect the UV bulbs. So here's the city of Monterey's water quality. You can see that they have PCE, TCE, and 1,4-dioxane at various concentrations, and they have a goal of non-detect, leaving the UV-AOP system, which they are currently achieving. So the good thing about the UV-AOP, it is that it is effective on other VOCs. So Monterey Park can use the UV-AOP for getting rid of the TCE, PCE, or 1,1-DCE. What we are seeing is that the peroxide dosage needed are much higher than what we've seen in potable reuse projects. So we're looking at greater than 10 micrograms per liter for these drinking water treatment plants versus 3 milligrams per liter at somewhere like Orange County Water District that has a groundwater replenishment project and who's been doing it for a long time, who's kind of been able to dial in what their needed dosages. The treatment plants do have GAC downstream, and that's really just for quenching the excess peroxide. And if you had a lower peroxide dose, you could actually use chlorine to quench. But for the drinking water treatment plants, we are seeing that they need to put in the GAC. One thing that's really important when you're doing a UV-AOP system is the hydroxyl scavenger demand. And that's understanding your water quality parameters is really key for addressing your treatment needs. And these parameters vary dramatically, not only by location, but they actually change over time. So it's important to have an ongoing monitoring program to understand how your treatment is going to be impacted as these change. The treatment cost for UV-AOP is extremely high. You can see for LADWP, their capital cost is quite high. And then even Monterey Park, it is a really high capital cost. And then on top of the high capital costs, you do have very high operation and maintenance costs. UV is really energy intensive, and so you pay a lot of money for energy. And then you have a high chemical cost with the peroxide. So some of the treatment considerations are you really want to understand your water quality parameters because those will have a huge impact on your treatment. And because of all that, we do recommend that pilot testing be done at your site and then full-scale demonstration testing once you're getting everything ready to go. Now kind of switching over into our potable reuse. So we do have regulations for both groundwater recharge and replenishment projects and surface water augmentation. However, our initial draft regulations didn't really address 1,4-dioxane. We did realize that this was a concern, especially in wastewater. And so we wanted to make sure that we were addressing it when we did have our regulations come out. So we do require full advanced treatment for groundwater recharge. So what is full advanced treatment? And that's where we require RO and UV-AOP. And so RO is really effective at removing very large particles or ionic compounds. And typically when you have a molecule with a molecular weight greater than 250, RO is fairly good at removing those. However, RO is much less effective at removing small non-ionic neutral compounds. And kind of thinking back to the properties that we went over, 1,4-dioxane definitely meets that. It only has a molecular weight of 88, and it's non-ionic, so it can definitely pass through the RO. And other things of concern are NDMA also. So that's why the UV AOP is important. And we do see in California that most of the potable reuse projects are using peroxide as the AOP, and that's because the peroxide does create a hydroxyl radical that will meet the half-log reduction in 1,4-dioxane that is required for the potable reuse projects. One thing that's difficult is to kind of optimize the peroxide dose, and it's difficult to do so because it's difficult to quantify the hydroxyl radicals because they're so short-lived and very, very reactive. And like I mentioned earlier, Orange County Water District, who has been doing this for a very long time, has been able to dial in theirs to about 3 parts per million. So right now, potable reuse do have to meet the 1 part per billion notification level, and that helps to make sure that we're not degrading either the groundwater aquifers or any of the surface water reservoirs. And while UV alone can photolize NDMA, 1,4-dioxane we've really found needs the AOP to really enhance that removal. And we think 1,4-dioxane is a really good indicator compound just because it does have some unique properties. It is going to get through the RO, but with the UV AOP, if we're not getting any detections out of that, we do assume that the UV AOP system is working appropriately and therefore eliminating any other chemical that could possibly get through that we're not able to measure. And with that, here are some of the resources that I used. And if there's any questions, I'll be happy to answer them.